Similarly, we can also use the eigenvalues to determine if the Hessian matrix is negative semi-definite or negative definite. That is, if all the eigenvalues of the Hessian matrix are non-positive, that is less than or equal to 0, then the Hessian matrix is negative semi-definite. As we discussed previously, if the Hessian matrix is negative semi-definite, then this function fx is concave. If all the eigenvalues of the Hessian matrix are negative, that is less than 0, then the Hessian matrix is negative definite. As we mentioned previously, if the Hessian matrix is negative definite, then this function fx is strictly concave. The eigenvalues of the Hessian matrix can be obtained using this equation. That is, the determinant of this matrix is equal to 0. Let's look at example 3. In this example, we want to determine if this function fx is convex or concave. We first calculate the partial derivatives with respect to each x. We first calculate the partial derivative of fx with respect to x1. That should be minus 4 times x1 plus 3 x2. We can also calculate the partial derivative of fx with respect to x2. That should be minus 8x2 plus 3x1 plus 5. Then we can calculate the second partial derivative of fx with respect to x1, which is equal to minus 4. We continue to calculate the second partial derivative with respect to x2. That should be equal to minus 8. We calculate the second partial derivative of fx with respect to x2 first, and then x1 is equal to the second partial derivative with respect to x1 first, and then x2. Both are equal to 3. Then we calculate the eigenvalues of this Hessian matrix. We get this equation. Then we obtain two different eigenvalues, lambda 1 and lambda 2, which is equal to minus 2.4 and minus 9.6. All eigenvalues are negative. That means this Hessian matrix is negative definite. Then we can confirm the function fx is strictly concave. Now we provide a summary on what we have discussed previously. That is the evaluation of convexity or concavity of a multi-variable function fx using the eigenvalues of the Hessian matrix. If all eigenvalues are positive, then the Hessian matrix is positive definite. The function fx is strictly convex. If all eigenvalues are non-negative, the Hessian matrix is positive semi-definite. The function fx convex. If all eigenvalues are non-positive, then the Hessian matrix is negative semi-definite. The function fx is concave. If all eigenvalues are negative, then the Hessian matrix is negative definite. The function fx is strictly concave. If some eigenvalues are positive and some eigenvalues are negative, then the Hessian matrix is indefinite. The function fx is neither convex nor concave. Please note that when we talk about convexity or concavity of a multi-variable function fx, the default domain of x is usually Rn. That means each variable xi in this multi-variable function fx can vary from negative infinity to positive infinity. If we have some specific restrictions on some variables xi, for instance x1 is greater than or equal to 1 and less than or equal to 3, then the domain of variable x is not Rn. Then how can we determine if a multi-variable function fx is convex or concave in this situation? This will be discussed later. If a function fx can be separated into the sum of two functions f1x plus f2x, then if both functions f1x and f2x are convex, we can conclude fx is convex. In other words, the sum of convex functions is also convex. If both functions f1x and f2x are concave, then we can determine the function fx is concave. In other words, the sum of concave functions is also concave. If f1x is concave and f2x is convex, or f1x is convex and f2x is concave, then we cannot determine the function fx is convex or concave based on these two functions f1x and f2x. In this situation, if we want to determine if the function fx is convex or concave, we need to calculate the eigenvalues of the Hessian matrix of this function fx. Based on the values of the eigenvalues, we can determine if the function fx is convex or concave. This has been discussed previously. Let's look at this example. In this example, fx is the sum of two functions. The first function is a1 times x1 minus c1 squared. The second function is a2 times x2 minus c2 squared. a1 and a2 are greater than or equal to 0. It is not too difficult to determine both functions are convex. Based on what we have discussed just now, the function fx is convex. This is because the function fx is the sum of two convex functions. Previously, we have discussed convex and concave functions. As an optimization problem is to find the optimal objective value in the feasible region. Then we also want to know if the feasible region is convex or not. Now we define a convex region. A region is convex if all the points on the line segment that joins any 2 points in the region are also in the region. In other words, we take 2 points in the region and use a line segment to join these 2 points. If all the points on the line segment are also in the region, then this region is convex. Based on this definition, it is easy to determine this region is convex. This is because we take any 2 points A and B in this region and use a line segment to join these 2 points. Then, all the points on the line segment are also in the region. Let's look at this region. This region is not convex. This is because we take 2 points A and B in this region and use a line segment to join these 2 points. Then we can see some points on the line segment do not lie in this region. Let's look at another region R, which is from minus infinity to positive infinity. This R region is also convex. This is because we can take any 2 points in this R region and use a line segment to join these 2 points. All the points on the line segment are also in this R region. How about the region Rn? This region is also convex. We can define a convex region mathematically. Let's use C to denote a convex region. We take any 2 points x1 and x2 in this region and use a line segment to join these 2 points x1 and x2. Then, any point on the line segment between these 2 points can be represented using this equation. In this equation, theta is a parameter which is between 0 and 1. When theta is equal to 0, then the point x is the point x2. When theta is equal to 1, then the point x is x1. When theta is between 0 and 1, then x is any point on the line segment between x1 and x2. Based on the definition of a convex region, any point x on the line segment between x1 and x2 should also belong to this region C. We can use this mathematical definition to check if a region is convex or not. However, this is not usually convenient. There is one convenient way that can be used to determine if a region is convex or not. Let's look at this theorem. A region is completely bounded by inequality constraints in the form of Gix is less than or equal to 0. That means the region is constructed by inequality constraints only. There are no equality constraints involved. If the constraint function Gix is convex, then the region is convex. A region is completely bounded by inequality constraints in the form of Gix is greater than or equal to 0 if the constraint function Gix is concave. Then the region is convex. This theorem provides 2 options to determine if a region completely bounded by inequality constraints is convex or not. To be clear and not confused, I suggest you use the first option. That is, all inequality constraints should be in the form of gix is less than or equal to 0. If some inequality constraints are in the form of gix is greater than or equal to 0, then we need to convert these inequality constraints into the inequality constraints in the form of gix less than or equal to 0 through multiplying both sides by -1. After that, we determine if the constraint function gix is convex based on the eigenvalues we have discussed previously. If the constraint function gix is convex, then the region is convex. Otherwise, the region is not convex. Let's look at this example. In this example, a region is bounded by these two constraints, these two inequality constraints. We want to determine if this region is convex or not. As we can see, the first inequality constraint is greater than or equal to. The second inequality constraint is less than or equal to. We first convert the first inequality constraint into less than or equal to by multiplying both sides by -1, then we can get this one. As we only have two inequality constraints, we can plot this region that is bounded by these two inequality constraints. From this graph, we can see the region is convex. Now, let's use that theorem to determine if this region is convex or not. After rearrangement of the first inequality constraint, both inequality constraints are in the form of gix is less than or equal to 0. Based on the first option of that theorem, we need to determine convexity of the function constraints g1x and g2x. We first need to determine if the constraint function g1x is convex or not. We can calculate the Hessian matrix of this constraint function g1x. We can get all eigenvalues, which are 2 and 0. Both are non-negative. That means the Hessian matrix is positive semi-definite. Then we can conclude g1x is convex. We can also calculate the Hessian matrix of the constraint function g2x. This is the Hessian matrix of g2x. It is not too difficult to get the eigenvalues, which are 0 and 0. Both are non-negative. That means the Hessian matrix of g2x is positive semi-definite. Then we can conclude g2x is convex. All constraint functions are convex. Based on the theorem, the region is convex. If a region is bounded by linear constraints, then this region is a convex region. The linear constraints can be linear equality constraints and linear inequality constraints. As we have learned linear programming optimization problem, the feasible region in linear programming optimization problem is convex. This is because all constraints are linear. Now we can define convexity of a feasible region. For a general optimization problem, we usually have the object function, equality constraints, and inequality constraints. A feasible region is usually constructed by equality constraints and inequality constraints. If the constraint function in the equality constraints are linear and the constraint function in the inequality constraints are convex, then the feasible region F is convex. If Hjx is not linear, then the feasible region F is generally not convex. This is because if Hjx is not linear, then the graph of Hjx is a curve like this. The feasible region F is all the points on this curve. If we take any 2 points on the curve and use a line segment to join these 2 points, then we can see not all the points on the line segment between these 2 points are on the curve. This is why we require Hjx are linear to ensure the feasible region is convex. We can use this conclusion to determine if a feasible region is convex or not. We have defined convexity or concavity of a function. We also defined convexity of a feasible region. Now we can define a convex optimization problem. In the minimization problem, if the function fx is convex, the equality constraints are linear, and the constraint functions in the inequality constraints that are in the form of gjx is less than or equal to 0 are convex. That means the feasible region is convex. Then this optimization problem is a convex optimization problem. In the maximization problem, if the object function is concave, all equality constraints are linear, and the constraint functions in the inequality constraints are convex. That means the feasible region is convex. Then this optimization problem is also a convex optimization problem. You can see the difference when we define a minimization problem and a maximization problem as a convex optimization problem. The only difference is related with the object function. In the minimization problem, the object function should be convex, while in the maximization problem, the object function should be concave. Finally, I also want to highlight that the inequality constraints should be in the form of djx is less than or equal to 0. If some inequality constraints are not in this form, that means some inequality constraints are in the form of gjx is greater than or equal to 0, then we can first convert into the form of djx is less than or equal to 0 through multiplying both sides of the inequality constraints by -1. Then we can make sure all inequality constraints are in the form of gjx is less than or equal to 0. If we have a convex optimization problem, then the local optimum is also the global optimum. In other words, for a convex optimization problem, if we find a local optimal solution, then this solution is also the global optimal solution. That means we can guarantee the global optimality for a convex optimization problem. Finally, we also want to discuss convexity or concavity of a function over a domain. As we have discussed previously, convexity or concavity of a function fx is usually defined over the domain of R or Rn. That means all variables can vary from negative infinity to positive infinity, if we have some specific restrictions on some variables, that means the domain of the variables is not R or Rn. Let's use C to denote the domain of the variables. How can we determine a function if a function is convex or concave over the domain of C? Let's look at one-dimensional function fx, and x is in the domain of C. We first check if the function fx is convex or concave over the domain of R, as we have done previously, and also we need to check if the domain C is convex or not. If the function fx is convex and the domain is convex, then the function fx is convex. Similarly, if the function fx is concave and the domain is convex, then this function fx is concave. Similarly, for a multi-variable function fx, x is in the domain of C, we first need to determine if the function fx is convex or concave over the domain Rn. We also need to check if the domain C is convex or not. If the multi-variable function fx is convex over domain Rn, and the specific domain C is convex, then this function fx is convex. If the function fx is concave over the domain Rn and C is convex, then the function fx is concave. From these statements, we can see if we have specific domain for a function fx and we want to determine if a function fx is convex or concave, the specific domain must be convex. This is also true when the domain is R or Rn. This is because R and Rn are also convex regions, as we mentioned before. In other words, the definition of a convex or concave function must be on a convex region. If the specific domain is not convex, then the function is usually neither convex nor concave. In this topic, we introduced the definition of convex and concave functions. When we talk about convexity or concavity of a function, the domain of the function is usually R or Rn. That means any variable in the function can vary from negative infinity to positive infinity. If we have some specific restrictions on some variables in the function, then the domain of the function is not R or Rn. That means we have specific domain for this function. In this situation, the specific domain over which a convex or concave function is defined must be convex. We also introduce the Hessian matrix and the necessary and sufficient conditions that can be used to determine convexity or concavity of a function. The convenient way to determine if a function is convex or concave is based on the second-order derivatives for one-dimensional functions or eigenvalues for multi-variable functions. After that, we introduce the definition of a convex region. If a region is constructed by the equality constraints in the form of hx is equal to 0 and the inequality constraints in the form of gx is less than or equal to 0, if the equality constraints are linear and the constraint function gx in the inequality constraints is convex, then the region is convex. I also want to mention a function can be convex or concave. However, the region can only be convex or non-convex. We cannot say a region is concave. This is because there is no definition of concavity of a region. Finally, we defined a convex optimization problem, which is very important. This is because for a convex optimization problem, any local optimal solution is the global optimal solution. We can guarantee global optimality for a convex optimization problem. If you understand all of them and know how to determine if a function is convex or concave, and if a region is convex or not, then you fully understand the key points in this topic. Thank you very much. See you next time.